Oh, it's my fault. There we go. Should start working now. Okay, so just to define what a fractal is, it's simply a geometric shape which are usually defined or drawn or generated using a set of recursive rules. Okay, so recursive rules mean we just simply apply them to themselves over and over again. So we dealt with recursive use of recursive functions when we looked at the flood fill algorithm. I said then, but recursive is generally bad programming practice. Unfortunately, when we're dealing with fractals, it's unavoidable. Why are we looking at fractals within sort of massive graphics and virtual environment? Well, as we'll see on Friday, we're going to use fractals to generate random terrain. So quite often in a virtual world, if you've got a massive virtual world and you're not going to sort of define each individual point, what we tend to do is develop random terrain generators. And we use fractals to do that. The reason why we can do random terrain generators is landscapes tend to have a self-similarity property, which is shared with fractals. And by self-similarity, I mean, if we sort of zoom in on a fractal shape or part of a fractal, the zoomed in part, and if we blow it up, it tends to resemble. It's also seen in landscapes, and the property is also seen in nature, for example, clouds, plants, etc. So in a minute, I'm just going to put up a slide which actually shows this self-similarity property. So that's why I'm talking about fractals today. We're going to be using them to sort of generate some random terrain. Today we're going to be looking at some popular fractals, some we've probably seen before. We're going to be looking at in detail how to generate these, and on Friday I'll be looking at how we do random landscape generators. And that will be your assignment 12, your final assignment for this unit. Okay, so here's some examples. Sort of unashamedly just went on the internet and did a bit of a Google image search. But as you can see, these, so if you look at frost, or I probably should have put a snowflake here, up here. When you see how frost crystals develop, they're very fractal in nature. So if I was to zoom in on, let's say, this sort of spur here, if I was to zoom in on that, it looks like the larger shape itself. This one I quite like down here, broccoli. Okay, if you take a broccoli, standard broccoli from the supermarket, I hope you all eat your vegetables and you no, okay. Well, if you go to the supermarket, go and buy a broccoli. If you snap a floret off, that kind of looks like the whole broccoli on itself. That's an example of self-similarity. And here we got fern. Okay, here's just a photograph of a fern. If we just consider one of these sort of stems from the fern, that kind of looks like the fern itself. If I was to zoom in on that. And that's what we kind of mean by self-similarity. Okay, so at different scales, it looks the same. When we're dealing with landscapes, if you think of a mountain, okay, the shape of a mountain, if you zoom in on like an outcrop or a little spike and blow that up, that also resembles a mountain. Now, if you go smaller scale, if you zoom in on a rock, like a boulder, zoom it up, often looks like a mountain, and you can keep going down to quite small scales. Okay. So that's self-similarity. Today we're going to be looking at sort of generation of fractals and some fractal properties, what they have. The simplest one is called the Cantor set. And this was devised by a guy called George Cantor, who's sort of, he's best known for really inventing set theory. And he was very interested in counting things and the nature of, okay, what happens when we start going to infinity. So have you heard about Aleph 0 and Aleph 1, size of infinities? Some infinities are greater than other infinities. So that's what Cantor was responsible for. Well, he So whenever we are going to have a look at fractals or fractal landscapes, when I say stage n equals 0, I mean, okay, what are we starting with? Now, we start with a straight line at stage n equals 0. And the rule is quite straightforward for the Cantor set, is we take away the middle third. So here we have our line. Okay, so this is at n equals 0. At each iteration, I'm going to remove the middle third of that line. So this line here, so instead of just one line, I have two lines with nothing in the middle third. So now I've got two lines, okay, and each of those two lines, I'm going to do the same thing again. I'm going to remove the middle third. Okay, and we keep going on until we get to a situation down here where the lines are quite narrow, and eventually they kind of look you can hardly perceptible. So the point here is, as n gets larger, the line segments get smaller. But what happens when n gets very large? Okay, so what happens to this fractal and the size of each line? And that's what Cantor was interested in. Okay, one quite interesting way in which we can have a look at the complexity of a fractal is what we call its fractal dimension. Okay, so any of you read Euclid's Elements? Probably one of the greatest mathematics texts ever. Okay, Euclid. He was interested in geometry, and in Euclid's Elements, he defined a point of being an object of dimension 1. Yeah, I've got to get this right. A line has dimension 2, plane. Point dimension 0, line dimension 1, plane dimension 2, etc. Now the fractal dimension is linked to that. So I actually think, okay, a 2D object, which we've been dealing with regarding polygons, is a plane. Okay, well, we can calculate the dimension of a fractal. Okay, so what we've got here is big N is the number of new elements which have been added at iteration n, little n, and epsilon is the scaling factor. So how much bigger or smaller are our new elements compared to what was already there? Okay, and we can define a fractal dimension in terms of a limit. Okay, so the limit as n, which is our iterations. So as the number of iterations gets very small, what is the ratio of the log of the number of new elements divided by the log of the scaling factor? Okay, for a 2D fractal, okay, the fractal dimension will be in the range somewhere between 1 and 2. Okay, the closer it is to 1, the more like a straight line we have. The closer it is to 2, the more like a plane. So it's going to be somewhere in between, and similar for a 3D fractal. Okay, so for example, let's have a look at the fractal dimension of the Cantor set. Okay, so number of new line segments, or number of line segments, at iteration 0, we just got one line. At the second iteration, we've got 2 lines. Sorry, at the first iteration, we've got 2 lines. Second iteration, we've got 4 lines. At the third, 8. So it's fairly easy to see, but we've got a general relationship of 2 to the power n number of lines. The length of the segment, okay, well, each time we're removing a middle third. So these 2 line segments are a third of the length of the original line segment. Okay, and this one here is 1/3 of the length of this line. Okay, so the length of the segment is simply a third multiplied by whatever it was in the previous iteration. So therefore, in relationship with the number of iterations, 3 to the power minus n is the length of the segment. So what does this mean for the fractal dimension? Okay, so using that formula, okay, so big N is 2 to the power n, epsilon was 1/3, or 3 to the power minus n. Okay, so using laws of logs, okay, take out the power, okay, so multiply the power in front of the log. Okay, so notice here we had a minus n, hence why this minus disappears. Okay, n over n, we'll divide both top and bottom by n, we get log 2 over log 3 to the power minus 1. Okay, which is simply log 2 over 3, which is 0.6309. Okay, so this means our Cantor set isn't even a line. It's somewhere between a point and a line. Okay, so that gives us some idea of what the Cantor set is. Cantor set, to be honest, is pretty boring. Not a lot you can do with it. So what I'm going to do now is move on to another example of a fractal, and this one's called the Koch snowflake. And this one's interesting because it's a shape with a finite area bounded by an infinite circumference. Another example of this is the coastline of Great Britain. Okay, so if you were to estimate the length of the coastline of Great Britain, you might use, let's say you get a ruler of 10 kilometre long. So let's say you've got a 10 kilometre long ruler and you outline the coast of Great Britain, you'll get a number, you'll get a figure. If you were to halve the length of your ruler and do it again, you'll get another value for the coastline, which will be longer. Okay, if you'll keep reducing the size of your ruler into sort of even the atomic scale, you'll keep getting a larger and larger coastline. So a coastline of an island is an example of a finite area bounded by an infinite curve. And the rules for generating the Koch snowflake, we start with an equilateral triangle, and for each edge of an equilateral triangle, we remove the middle third and replace it with two lines which form an equilateral triangle themselves. Okay, so place an equilateral triangle so its base fixes along the middle length and just remove the middle length. Okay, so for a single side of your triangle, this is what we have. So we start off with a straight line. Okay, remove the middle third and replace it with an equilateral triangle. And if we do, here we've got 4 lines. For each of these 4 lines, if we do exactly the same, okay, you can see we have the number of lines is again multiplied by 4. Okay, so there's 16 different line segments there. Okay, I believe in the notes I've given you, well, I've sort of written some MATLAB code. If you're interested in generating these, you can go away and type in that code and have a look. It's not something which we'll be assessing you on. It's just more of a curiosity. Okay, so that's a stage 1 inverted triangle. Oh, sorry, stage 0. Stage 1. Okay, so we've replaced the middle third with our equilateral triangles and just removed the bottom edge of each triangle. Okay, so now for each of these edges, we do the same thing. Okay, so for each of those edges, you can see I've replaced those with a triangle. And we can keep going, and notice the sizes of our edges or our lines get smaller and smaller each time. So I think I've gone up to about stage 5 there. Any more and you could probably not detect, it's too small for us to be able to see any difference. So that's a Koch snowflake. Okay, let's have a look at fractal dimension. Slightly more complicated than the Cantor set. So what I've done here is I've tabulated the number of iterations, the number of sides, which in other words, the number of straight lines, and the length of these sides. So I'm going to assume the sides are a length 1 to start with. Okay, well, in the first iteration, each of my 3 sides has been replaced by 4 lines. So the number of sides I have is now 3 times 4. And the length of these sides is each 1/3 of what the original one was. Okay, so that's iteration 1. Iteration 2, now I've got 12 sides. Each of those 12 sides is going to be replaced by 4 lines. So the number of sides I have now is 3 times 4 times 4, which is 36. Yeah, no, 48. So now I've got 48 sides, and each side is a length 1/27. So if my original side was length 1, now each of my 3 sides now is length 1/27. Okay. Iteration 3, you simply multiply the number of sides by 4 again, and divide the length of the sides by 3. And so we start to see a pattern. Okay, the number of sides added, and the length of those sides added. Okay, so after n iterations, Okay, the number of sides is 3 times 4 to the power n, and the length of those sides will be 3 to the power minus n. Okay, so that gives us the information I need to calculate the fractal dimension. Okay, so using the fractal dimension, okay, so on the top we have log 3 times 4 to the power n, and then the bottom we have log 1/3 to the power n. Okay, again using laws of logarithms and a bit of knowledge of limits. Okay, well I could split the log on the numerator. Okay, using laws of logs I can split them up, and if I bring down the power in front of the log. Okay, so therefore I can split up the limits. So remember all your work from last year in maths fundamentals with limits. Okay, so here we've got a limit of log 3 over n log 3. Well, log 3 over log 3 is just 1. So that's log of 1 over n. But as n tends to infinity, that's going to just disappear to 0. Okay, so that first limit, as n gets very, very large, it's going to get very, very small, that number. And so that first one is just 0. The second one, well, we end up with n over n. Now, if we divide both top and bottom by n, you just get log 4 over log 3. So there's no n involved there. So that gives us our limit there. So in other words, the fractal dimension of the Koch snowflake is just 1.2619. So what does that mean? This means it's closer to being a line than it is to being a plane. Okay, so our Koch snowflake, remember the fractal dimension of a straight line is 1, dimension of a plane is 2. So it's closer to being a line than it is to being a plane. What's useful about or interesting about the Koch snowflake, it's an infinite circumference bounding a finite area. Okay, the next one, which tends to be the sort of one of the common ones, the popular ones you see, something called the Sierpinski triangle. Okay, this is kind of a nice sort of nice design. It's named after a Polish mathematician, but it's actually been seen in some medieval castles and churches and what have you, as just like a nice mosaic type pattern. Okay, so the scheme for the Sierpinski triangle is we start with a filled equilateral triangle at stage 0, and for each iteration you take a filled triangle, okay, make a copy, halve the size of that copy, turn it upside down and place it in the middle. Okay, so that's your stage 0, that's what we start with. So a filled equilateral triangle, and what I've done here is I've made a copy of it, halved the size, and then placed it upside down in the center of that triangle. So at the first iteration, it now looks like, well, we now have 3 triangles, 3 filled triangles. And for each of these filled ones, we do the same. Make a copy, turn it upside down, halve the size, and plonk it in the middle. Okay, so, and we do the same for each of these triangles, etc., and so on and so forth. Okay, so again, in the notes, there is some MATLAB code to do this. I've got to admit, it actually took me ages to calculate this on MATLAB. It's not easy. It uses recursive calls, which are kind of, they give you a headache if you try and program in them. But I've given you the code if you want to have a play around with them. And you could also do other things like Sierpinski squares. Okay, anybody? No, you probably haven't seen it. If you've been to my office, and there's a what's called a Menger sponge, which is one made out of train tickets. Okay, I don't know. Have you ever heard of Menger sponge? Oh, right. Menger sponge is essentially a 3D version of the Sierpinski square. So you take a square, remove the middle square. So if you have a 3D version, you have a cube, and you remove the middle sort of section, and you make what's called a Menger sponge. They were doing something about it in the Museum of Science and Industry with schools just before Christmas. Anyway, the reason why I wanted to show you the Sierpinski triangle is because there is another way of defining or generating this Sierpinski triangle. And this is called the chaos game. Okay, so we've already looked at the geometric way of doing it. take a triangle, remove the middle triangle, and keep doing it. An alternative way of doing it, which we're going to be using probably not today, but on Friday to have a look at ferns, is a chaos game. And this is all about random probability. Okay, so if you start at a point somewhere on your Sierpinski triangle, so I normally start at one of the 3 corners, what we do is we randomly select one of the 3 vertices of a triangle. So I don't know whether you can you have a no, I can't. So you take your random. I was going to say flip a coin, but obviously you need a random number. Randomly select between 3. So use a random number generator. If your random number is less than a third, you choose 1 point. If it's between a third and 2/3, you choose the other. Okay, and what we do is you find a point which is halfway between the point you're currently at and the corner of the triangle you've chosen. And then you mark that point. And then you do the same thing again. You choose randomly one of the other vertices. Go halfway to that, mark it, and then you sort of choose again. So if you have a point which is at coordinates x and y, or xn, yn, the coordinates of the current point, if you've chosen to go towards the bottom left corner, okay, the new point is at a half of your current coordinates. So what we can do is we can write this as a matrix equation. Okay, so this is your x and y. Okay, so we have some transformation matrix multiplied by your current coordinates. Okay, well, if you chose the top vertex and you're currently at xn, yn, the point halfway between your current location and the top vertex is these coordinates. So if you write this in matrix form, we have your transformation matrix plus some vector. Okay, note that this matrix here, the square one, is the same for all three coordinates. Else, if the bottom right vertex is chosen, then the coordinates of the new point is at half xn plus 1 and yn. Okay, so that's calculated using that matrix equation. So this is actually quite easy to code. Okay, you just loop through lots and lots of points, generate a random number. If the random number is between 0 and a third, you calculate this. If it's between 1/3 and 2/3, you calculate the second one. Or if it's greater than 2/3, you calculate the third one. Okay, so if you do that for 1,000 times, this is what you should get. Now these, I mean, you'll get something different because obviously we've got a random number, but you can sort of see that we've got a pattern emerging there. Okay, so there are 1,000 dots there. I've done it 1,000 times, and you can kind of see a pattern. If we do it for 10,000 iterations, you can see, all right, we can sort of start to recognize we've got the Sierpinski triangle. And if you do it for 100,000, we got a fairly good representation of the Sierpinski triangle. This is an example of a chaos game. Okay, it's a random element there, and we have some transformation on our coordinates, and we mark the point. And we're going to use this as well. You could use this to generate fractal ferns, which we'll discuss on Friday. Okay, right. To finish off this lecture, I'm going to sort of look at what I think is the daddy of all fractals. It's kind of like the one which is most common, most popular, and it's the one you've probably seen quite a few times before. And it's called the Mandelbrot set, named after Benoit Mandelbrot, who sort of coined the term fractal. And I don't want to sort of be too disparaging, but it's a pretty picture, but there's not a lot of sort of significance to it. But we're going to look at it anyway because it is kind of it is a pretty picture, and that's what sort of graphics is all about, making things look nice. So Benoit Mandelbrot, who actually coined the term fractal in the late 70s, he wrote a book, Fractal Geometry of Nature, where he's kind of obsessed with how clouds and things look, sort of like a geometric pattern. You may have seen it. Anybody watch QI? Yeah, oh, I took a screen grab from the opening credits. Okay, I'm not that sad. It's only on YouTube. You know, I didn't sort of stay there with my phone taking a picture. This is just on YouTube. Just took a screen grab. This image here is actually the Mandelbrot set, and it's appeared in Futurama, Simpsons, Big Bang Theory. You know, it sort of comes up in a lot of popular culture. So that's why I thought we'd have a look at it, and it's kind of a quite nice thing to look at. Right, so we're going to look at the generation of the Mandelbrot set, and this is done using complex numbers. Now, for some strange reasons, students tend to see the word complex numbers and then run a mile. Okay, they're nothing to be scared of. Okay, Mandelbrot set is defined using these complex numbers. Okay, I know you should have seen these before in previous studies, but just do a bit of recap here. Okay, a complex number is of the form a plus bi. Okay, that's what a complex number is. It's just a, which is a real number, plus b, which is another real number, multiplied by I, which is what we call an imaginary number. Okay, and imagine I squared is equal to -1. Now, these imaginary numbers allow us to do all sorts of things in mathematics. So, for example, solving a quadratic. Sometimes if you use quadratic formula, you get a negative discriminant. Well, imaginary numbers allow us to sort of take that into account. Okay, they're a huge relevance to all areas of mathematics. The a in this number is known as a real part. Okay, so a is known as a real part of z and denoted by REZ. And b, the coefficient of I, is known as the imaginary part. Okay, and that's denoted by imz. Okay, so I is your imaginary number. Your a plus bi is your complex number. Okay, and we could do some operations on these. So addition. Okay, if you're adding two complex numbers, add the real part together and add the imaginary part together separately. So here we've got two imaginary numbers. Okay, so 2 plus 3i plus 4 minus 2i. If we add the real parts together, we've got 2 plus 4. Add the imaginary parts together, we've got 3 minus 2. And so our complex number left, we end up with is 6 plus I. Okay, the product is slightly more complicated. Okay, so for the product, we have to expand out some brackets. Okay, so if I've got the same two complex numbers, okay, and just as you would if these were algebra, expand out the brackets. Okay, so we have 8 minus 4i, so that's 2 times 4, 2 times minus 2i. 3i times 4 is 12i. Now 3i times 2i is minus 6i squared. Now remember, I squared is equal to -1. So instead of minus 6i squared, you just get plus 6. Okay, and so eventually we get 14 plus 8i. Okay, so that's how we sum and product complex numbers. By the way, MATLAB can deal with complex numbers quite easily. One thing I would say is when you're defining your imaginary number, use a 1, then an I. Okay, both methods will work, but sometimes if you use just the I in MATLAB, it will sort of throw a hissy fit. So always try and use 1 I on it. Okay, the Mandelbrot set is defined in what we call the complex plane. Now this is simply a set of axes or a plane where the horizontal axis is the real part of your complex number, and the vertical axis here is the imaginary part of the complex number. So if you've got a number a plus bi, okay, that could be plotted on the complex plane at that point with the real part a and the imaginary part b. So that's what we're going to use to plot our Mandelbrot set on. And the last sort of bit of the recap, we need to know about the modulus of the complex number. This sort of gives you an idea of the size of a complex number. And the modulus is sort of denoted similar to a norm, okay, with simply or a magnitude of a vector with vertical lines either side of your complex number. And it's simply the distance between the number when plotted on the complex plane and the origin of the complex plane. And we can calculate this using Pythag. Okay, so if you've got this point here, this is my complex number, real part B, real part A, imaginary part B, the length of the distance between the origin and our number, simply square root A squared plus B squared. When we're constructing the Mandelbrot set, we don't need to do any of this. MATLAB will do it all for you. In MATLAB, we use command ABS, so ABS is your MATLAB command for the modulus. Okay, so with that sort of, so we know that we're dealing with the complex plane and we're dealing with complex numbers. How do we define the Mandelbrot set? Well, this is kind of rather, I think, rather beautiful. Okay, it's such a very, very simple scheme. And we have an iterative scheme where if we start with our number C, now C is a complex number somewhere in that complex plane. And what we're going to do is we're going to apply this iterative scheme. We're going to square a number Z and add it to our number C. And so that's the next value. So Z, Zn plus 1 is equal to Zn squared plus C. So as we update, as we iterate, Z will keep changing. Okay. If the modulus of Z remains bounded, in other words, it just doesn't fly off to infinity, it remains bounded, our point C is in the Mandelbrot set. Okay, so it's all about that point C. So Z is just what we calculate, C is what we're testing. We start Z off as 0. So Z1 will just be C. Z2 will be whatever C was squared plus C. And we keep applying the same thing. We say C is said to have escaped. Okay, I can't think of really another word for it. It means it just disappears off. The modulus of Z becomes too large. So C is said to have escaped if the modulus of Z is larger than some escape radius. And we tend to use 2 for that. Okay. So let's have a look at 2 such points C. So let's start C is equal to 1. So real part 1, imaginary part 0. So that's just the number 1 on the so that's on the horizontal axes. Okay, so Z0, 1 plus, well, that's C. Okay. Z1 will be whatever your Z0 is squared plus C. Okay, so we're going to have to square this. Well, that's quite easy. That's just 1 squared. Okay, so 1 squared plus 1 plus 0 gives me 2. So the modulus of Z1 is equal to 2. Okay, do the same thing again. Z1 is 2, so square 2, I get 4. Add C, which was 1, I get 5. So the modulus of Z2 is 5. Okay, and I can keep going. So this one's quite easy because there's a 0 imaginary part. So you can see after only 1 iteration, we've already got to the escape radius. So if I'm using 2 as the escape radius, here, our point C is already escaped. It's not in the Mandelbrot set. So anything with a modulus of greater than 2, we say it's not in the Mandelbrot set. But what about a different number? Let's say we've got the number I. So our complex number is 0 plus I. So we're starting with 0 plus I, and our modulus is 1. Okay. So we take our previous value of Z, square it, and add C. Now here, obviously, we've got I squared, which is minus 1. Okay, so that's minus 1 plus our value of C, which is I. Modulus of this, 1 squared plus 1 squared is 2. So we have square root of 2. Okay, do it again. So our Z1 now is minus 1 plus I. So minus 1 plus I squared is going to be 1 minus 2I minus 1. Okay, so that's 1, because that's minus 1 times 1. 2 lots of minus 1 times I, and then I've got I squared. Now I squared is simply minus 1. Add that to my original value of C, and I get minus I, which has got a modulus of 1. Okay. Now the third number in the sequence, okay, minus I squared, okay, is minus 1, plus I gives me minus 1 plus I. Now that's the same as Z1. Okay. And what you'll notice is as you go on, we keep cycling between minus 1 plus I and minus I. Minus 1 plus I, etc. So that, I can go on forever. That will never escape. So the modulus is always less than 2. So therefore I can say that that is in the Mandelbrot set. Okay, so if we do the same for lots and lots of points. So here I've got my C is in the range real parts minus 2 to 1. My imaginary parts are about minus sort of 1.2 to plus 1.2. And what I've done here is I've drawn a point in black if it's a member of the Mandelbrot set. It's in white if it escapes somewhere. Okay, and that's a Mandelbrot set. Okay, doesn't look that impressive compared to the ones you may have seen before. The reason being is because only the points which are in it have been plotted. Any points which are outside the Mandelbrot set have been ignored. But what I can do is I can include the ones outside the Mandelbrot set in with my plot. Okay. Oh, before that, actually, I'm going to look at the convergence behavior. Okay, so let's take a point. I've chosen minus a half plus a half I, which is here. And what I'm going to do is I'm going to show you what happens to that point as we iterate. Okay, so we start there. The first iteration, we move to here. So this is our Z value. Okay, so using that Z value, square it, add C, we go up to there. Okay, and if I keep doing this, okay, all I'm doing here is just keep going through the iteration. We can see, but it always remains within the Mandelbrot set. Okay, so for any point which is drawn in black, the same thing will happen. That will always remain modulus less than 2. Well, if I move the point just slightly to the left, so instead of minus a half, I got minus 0.6. This is outside the Mandelbrot set. If I do the same thing again, iterate through, okay, all right, that's inside. So is that. Okay, that's still inside, but we're starting to get sort of a bit further and further away. Okay, and as we carry on, you can see the modulus is going to get big, and eventually it will just bugger off. Okay, so that's gone outside. Okay, so that sort of gives you an idea of the convergence behavior. Okay, so that's Mandelbrot set. Okay, we can make it a bit more arty-farty by adding some colors. Okay, well, what these colors mean, they're not just put there to be pretty. What they are is they're dependent on how quickly a point diverges, we're going to color it a particular color. So if a point diverges very slowly, we think of it as being quite close to our Mandelbrot set. Where if it diverges very, very quickly, we think of it as being far away from our set. Now, I've got a couple of images I'm going to show you. One is with just using the iteration count. So if a point diverged after 40 iterations, I would have colored it one color. If it was after 50, I would have done it another color. But what you can also do is normalize this iteration count. And what this has the effect of is smoothing out the colors. Okay, so this is our Mandelbrot set. And this is with a color map applied. So for example, the red points are actually quite close to the Mandelbrot set, and they took quite a long time to diverge, where the blue points diverge very, very quickly. So that sort of gives you some idea of what's happening. If I normalize the iteration count, so that's just if M is my iteration count. Okay, if I apply this this sort of normalization expression, what happens? We go from this, which is kind of banded, to this, which looks smooth. Okay, so you can see that's a lot better, better image. Okay, and that's what you tend to find on